All right, thank you very much for coming, and especially, of course, the organizers, and especially even Max, because he insisted I would come. I was saying, no, I'm not going to come, and he made it possible for me to come, so thanks. And although I have not worked for a long time in this field, it was good to see a lot of old friends and people that I haven't seen for a long time, and see that such many nice topics have come to the fore since perhaps the last time I came to an algebraic, real or ordered conference. So since I'm being taped, I'm going to use my fancy chalk, so all the way from Japan. So the talk is going to be, the title is O-minimalism. And I apologize for those that have already heard it, because that was 3 years ago, and since then I've not done anything on this, so it's going to be exactly the same. So what does this O-minimalism mean? Well, first, I'm thinking of the models or the structures I'm looking at I called o-minimalish. And so o-minimalism is the study of o-minimalish structures. So what do I mean with that? Well, for those that know me better, they know that if I see something, I like to take an ultraproduct of that. Okay, so if I see an o-minimal theory, an o-minimal structure, and I take an alter power of that, that is o-minimal again. So I was happy for a long, long time. And in fact, at some point I thought, that's probably what always happens. You take alter products of o-minimal structures, you get o-minimal structure. And it took, of course, Lau to point out to me that's not true. And o-minimal theories, to be o-minimal is not a first-order property. So what is it then? So what you get if you take an alter product of different o-minimal structures? What do you get? What are properties what are still there of this structure that might be interesting, and you expect that at least a lot of o-minimality should be preserved in alter products. And independently, when I was working on this topic or thinking about this, there's a student of Scanlon Rennett, or Alex René, I don't know how to pronounce his name, who have worked on this, and Ono Fornaciero was also working on this, so all independent, and a lot of that was overlap. So, but at some point, I wrote it all down. There's one paper in the Journal of Symbolic Algebra, Symbolic Logic on this one. Okay, so what I mean, so let me be more precise. Okay, let me put it here. So I have some language with an order and all the usual stuff, but for simplicity, let me just assume that it has a ring structure, a field. So all my models are going to be fields, but it doesn't necessarily have to be for what I say, but it's just easier if I restrict to fields, ordered fields with some more structure. And so T o-min is the collection of all sentences that are true in any o-minimal L structure. So C is a sentence true in any o-minimal L structure. Wait, I should write bigger, right? And then a model of this I call o-minimalish. And there are two first-order properties that are in this theory that are readily there and people know them and were well studied, which I call, well, both are actually axiom schemes. They're not sentences, they're axiom schemes. So DC is definably complete. Complete, of course, means for the reals means that every unbounded set has a supremum, and definably complete means that every definable unbounded set has a supremum. Bounded, yes. Sorry. And this is equivalent, Chris Miller showed this, I think, that with, for instance, the intermediate value theorem holding, and also with something he calls definably connectness. And then the other scheme is what I call type completeness. And so that means that for any A, and okay, I say my structures are always going to be fields for simplicity. And so for any A in R, but I often also want to include the endpoints, look at the following type. For every b less than a, so this is a type depending on a, well, a partial type in principle. So this collection of sentences, b less than x less than a, and the claim type completeness says that this is a complete type. So every formula or its negation belongs to it. Or equivalently, you can say this actually means, for those that know this, this is equivalent with what they call local or minimal. So around each point, the structure is, well, in one dimension, is an interval, but including at the endpoints. But again, since you're field, you don't really have to worry about the endpoints. So these two properties, and note, of course, these are, definably complete, and it's enough here for one variable formulas. And this is also a one variable formula condition. And I do not know whether this is, see, the strength of minimality to me, and of minimality of whatever type of minimality you think of, is that you impose a certain constraint on the type of subsets of the line, and that has a major influence or restriction to what the subsets in higher dimensions can be. So the good question is it possible to is there an action system for o-minimality that only consists of conditions on one variable form, on one variable sets? Now, at some point, you could ask, is this perhaps enough? Does this give me o-minimality, the o-minimalism? But the answer is no, I learned, because Rennert apparently showed that, in fact, there cannot be a recursive action system for o-minimality. And these are rather very straightforwardly seen to be recursive. So there are kind of, it's probably very hard, therefore, to get a good system. Well, it's not recursive, so. Nonetheless, just these two give me already a very good theory. For instance, under this, so under DCTC, you have that, for instance, okay, so here's a theorem, a structure, and let me always say a field, an ordered field, an expansion of an ordered field is a model of DCTC, even only if, and here's a condition on the one variable sets, for all x in R definable, x is a union of intervals and a discrete set. Moreover, the union of intervals, I could take the barycenters, and that's also a definable set, and since it has no interior, it must be discrete. So, in other words, a better way to say this is that X is, as in o-minimality, you have such a set would be, if the structure would be o-minimal, X would be a finite union of intervals and points. And now it is a discrete union of intervals and points. And so, in a kind of a leitmotif or something is that many things are true if you replace finite by discrete. Now, discrete might be bad, but under DCTC, automatically, so in the model of DCTC, discrete is always bounded and closed. So that's another two properties a discrete set has. In particular, if you're a model of DCTC and the underlying field or the underlying order is that of the reals, which is locally compact, every discrete closed bounded set is finite. And so you're o-minimal. So models of o-minimalism are only the interesting models of the non-o-minimal structure that are o-minimalish have to be non-standard. Okay, so it's actually a non-standard notion, therefore. Moreover, in this DCTC, so I'm going to do the DCTC part here, we have a good notion of dimension theory. Well, let me not go too much in the details of it because others have worked on this, but what I would like to say is that one thing perhaps that I should mention is that Where is it here? Yeah, cell decomposition. Yes, that's what I want to say. Now, there are many attempts, or many, attempts is not the right word, many people have gone beyond o-minimality because a lot of structures are not o-minimal, yet interesting, and therefore developed a theory in that context, like local o-minimality, weak o-minimality, and deep minimality, and well, every letter of the alphabet minimality. And each time, of course, the test case is cell decomposition. But to my mind, many cheat because what they call a cell is a rather ugly thing, where for me a cell should be extremely simple. It's a cell, right? Not a multi-cell organism, but really a simple cell. So when I say cell, I mean cell. So a cell is for me what in any order structure cell should be. It's like, say, in 2 dimensions, we have either the graph on an interval, an open interval, or unbounded perhaps on one side, of a continuous and definable set, or a region between such 2 things. So that's what cells should be, and it's easy to say what this would be in higher dimensions. That's what a cell should be. But of course, you cannot expect now, what is then a cell decomposition? It cannot be that any definable set is just a finite union of cells, because that would, here it's a discrete union of cells, therefore. Unfortunately, I cannot prove that yet. I'm kind of confident it might be true. I'll say something more about that. So I have to weaken the notion of cell a little bit. And so the notion of quasi-cell, instead of definable, I'm going to say locally definable. So F is in this definition, and you can imagine how it goes in more dimensions. All the functions should be locally definable. And you can imagine what it means, right? And so with that notion, I can prove a cell decomposition under DCTC, which is, of course, too weak anyway. So probably if you put more, you can do better. But under DCTC, you can prove the following form of cell decomposition. If X is definable, any arity, any dimension, then there exists a definable set, a definable map into a discrete set. Remember, discrete is supposed to be finite in our case, right? And in fact, you can make that precise. Discrete is exactly the property of a finite set in an o-minimal theory. That's the theory of a finite set in o-minimal theories is exactly to be discrete. Such that each fiber is its quasi-cell. Of course, the fibers partition the whole thing, so you get a partitioning into cells and in a non-trivial way. Of course, you could write everything as a union of singletons, but that's kind of trivial. That's not what you want. But this is, as I said, not what I want, because I want cells to be cells, not quasi-cells. So you have to give this a name. The thing that you want, you give it a name, and then you see what happens. Now, I tried to, I'm sorry, I really tried to, I was going to call it tame. But the referee says, no, you cannot use the word tame. Everybody uses tame, there's too many uses of tame. So at the last moment, I had to change this, and I call this now, apologize, eukaryote. I'm sure that it has never yet been used anywhere in mathematics, so. So I call X, yo is well, right? And karyo means cell or core, center. So well-centered, well-cored, well-celled, I don't know. Something like that, yeah. So a subset X, a definable subset, is eukaryote if there exists a C from X to D, definable, plus definable and sorry, this is definable and this is discrete, such that the fibers are cells. So what you would want, up to the fact that it's not finite but discretely many. But remember, discrete is closed and bounded, so it's not Z or something. I mean, yeah, so it's kind of nice. So at the moment, I don't know whether o-minimalism implies that everything is eukaryote, or vice versa. I don't know exactly what the status is. And I'm a bit hopeful. I mean, Alf Dulwich, if for those that are in Humanity will know him, he's, to me, the master of counterexamples. And he claimed 3 times, oh, he have a counterexample, I'm close to getting it, and he couldn't actually figure it out. So I'm hoping that that's a good sign that it might actually be true, that o-minimalism at least, so the theory of o-minimality, implies eukaryote. So what good evidence we have for eukaryote? So okay, so this is what, sorry, I should have made one more definition. I call a structure eukaryote if all its definable subsets are eukaryote. Now, why do I single out the definition for a single subset? Because you could always look at all the eukaryote subsets in your structure. It might be not everything, or not all the definable subsets, but at least there's a good collection there. And that collection is actually closed under all Boolean operations, but also under projections. And therefore, there's a reduct that is first order, the eukaryote reduct. So every structure R has a eukaryote reduct. So RU is a reduct. And moreover, if R is a model of the o-minimality, is o-minimalish, okay, not o-minimal, but o-minimalish, then so is its eukaryote reduct. Is o-minimalish. Well, is a model of T. So I find it at least some good evidence, and I will give some examples of eukaryote structures later, if I ever get there, but okay. So now I want to study a bit more o-minimalist structures. And so I need what I want is an invariant or something, a measure of how far is a structure, an o-minimalist structure from being o-minimal. And the answer to that is through the notion of a Grothendieck ring. Now, I don't know whether I should define this, but let me very quickly define it, because I'm sure that it's not such a common tool yet in model theory. But in any structure, any first-order structure, you can define its Grothendieck ring. Namely, first of all, you have to say that two definable sets are definably isomorphic if, homework, fill in the blanks. And now I'm going to make the free group No, it doesn't have to be continuous. Actually, that's a good. There are 2 notions actually, and you can go 2 different theories for that. But yeah, let's now say not continuous, not necessarily continuous. So you take a free group on all definable isomorphism classes, and you mod out by the so-called scissor relations. And so a scissor relation is what it is. You take a set and cut it in 2, and you paste it together. So. Or a bit more general, is that the class of X plus the class of Y is the class of X intersect Y plus the class X union Y. It's a generalized counting principle. Right? It's a generalized Euler characteristic, to be even more precise. That's the scissor relations. That gives you a group. And now you make it into a ring, so the multiplication. X times Y is just a Cartesian product, the class of the Cartesian product. I prefer to do it with sets rather than with formulas, but technically you should do it with formulas. But it's more telling this way. Now, of course, since X cross singleton is definably isomorphic with itself, that means if you put now brackets around everything, this times the bracket of this little guy is itself. So this little guy, the bracket of that is just 1. It's a unit for multiplication. So 1 is the class of a singleton. Okay, so now here's the theorem, the first theorem that sets apart o-minimality from o-minimalism. So if R is o-minimalish, then R is o-minimal if and only if the Grothendieck, I didn't give a notation, okay. The gr is whatever was on the previous board of R is the integers. Of course, if you have, so let's see where do the integers come from. Well, you can take 2 points, and then the class of 2 points, if they are disjoint, is 1 plus 1, so you get all the, and so on. And then negative, where the negatives come from. Okay, so let me give you a little bit of a proof here. Well, I'm not going to prove the whole thing, but this direction, okay, Lau, you have to correct me if not, but I heard first of it, and it kind of took me by surprise, was when Deneuve and Leuser talked about it a long time ago. But I know it's in your book, so I don't know who was first with it. That if you're a minimal, then the Grothendieck ring is just Z. Oh, I don't know. But so I contributed to Deneuve and Leuser, but the D was also stuff for Van den Dries. And L for Lau. And it's very easy. Just that's the only thing I can do quickly. It's not so hard to see that some easy maps that map R into a single interval. So they have the same class. And so a single interval I can break up into halfway. Into this. Each of these 3 intervals are clearly isomorphic, so they have the same class. Let's call that L, the Lipschitz. So that's the class of the whole thing, which is the class of any interval. So you get L is equal to L plus 1. Remember, that's just a point. Is equal to L. Okay, and so this shows me that L is equal to -1. And that's where the negative comes from. And now, how do you do it in general? Well, look at the cell. Project down, this is definably isomorphic with an interval, so it has also, the class is also -1. If you have a cell like this, it's kind of definably isomorphic with one interval cross another interval. So it is -1 times -1 is 1. And cell decomposition says you have finally many of those. So that's how you get Z. And in fact, the value that you get is exactly the Euler characteristic in a topological sense. Remember the Gauss-Bonnet? I think it's Gauss-Bonnet, right? So how do you call Euler characteristic? The number of faces, 1, minus the number of edges, 1, 2, 3, 4, plus the number of vertices, also 4, which gives you 1. So this has Euler characteristic 1. Sorry? Yeah, okay, yeah, of course, yeah. But you can always flip things over with 1 over x to make it bounded and so, but yes. I know, I'm going a bit fast, but I mean, everything works. Don't worry about, the unbounded case always works, the unbounded parts. Okay, the other direction, of course, is not so trivial. I mean, it's not hard, but there's something to be done. So that at least gives you a criterion for something to be o-minimal or not. Another criterion now derived from this. No, it's much bigger. Yeah, no, it's not like the p-adics. In the p-adics, everything collapses and it's really just nothing, right? No, but here not. So, okay, so another theorem. What's the next theorem that you have in o-minimality? A nice result, all of this, of course, all in Lau's book, is that this relation here, to be definably isomorphic, is in an o-minimal structure, equivalent with having the same dimension and having the same Euler characteristic. But I told you it's the same like this, right? So this is these two conditions together make this, they give this equivalence. So what's the case in o-minimalism theorem? If two definable sets have the same, so this x and y are in, well, in perhaps different, we are working in our theory o-min. X and y are definable subsets with the same class and the same dimension. I already told you there is a good dimension theorem in DCTC. So clearly in T o-minimal has even a better dimension theory, I guess. If and only if they are isomorphic in some elementary extension. There's a definable map that is bijection, a definable bijection. No, you could add to it or not, and it gives a bit different things. Yeah, it gives you sometimes it's the same, sometimes it's not. In a minimal case? Yeah, but no, yes, it is because okay. In a minimal, because there it's always possible. Yeah, okay. Okay. Since I'm being taped, I have to be safe. So everything is now homeomorphism. Okay. Definable isomorphism, homeomorphism. Okay. I said it doesn't make so much difference. Sorry. Characteristic zero. Everything is in characteristic zero, right? Because it's ordered, yeah? So in some elementary extension, so it is, you might have to go a bit further to find the formula, to make the formula work. Yeah, definable is also always with parameters. Definable subsets are of course always defined with parameters. Okay, next theorem. Go back now to my favorite pet, the ultraproducts. So you have now, let's say, o-minimal fields. Okay, all our eyes are o-minimal, and if you read my book, this is the notation. This is their ultraproduct, and of course, this will be only a model of o-minimality. Will only o-minimalism, sorry. It will be a model of o-minimalism. But the structures themselves are o-minimal. So the question is, when is this actually o-minimal? So theorem, well, okay, theorem. R natural is o-minimal, even only if, for every formula, phi, there exists a bound n phi, such that the Euler characteristic. Oh, okay, I'm trying to squeeze. I'll squeeze it in.
Are you assuming that R is already o-minimal?
No. Our eyes are minimal, and this is their ultraproduct. Yeah. This is subscript. This is R natural. No, this is the colon. Okay, there is a bound such that for almost all I, okay, what am I saying? The Euler characteristic of the definable subset in the ith component is at most n. So in each component have this, the phi defines in each component a definable subset. If these Euler characteristics of these definable subsets are bounded, okay, independent of the structure, but depending on the formula necessary, then the structure is o-minimal. If you have this kind of uniform bound across the different structures. So the simple counterexample, to give an example of a structure that is o-minimalish but not o-minimal, take the reals and add a predicate and let Ri, a unary predicate, and Ri be the set of 0, 1 up to I. In Ri, this is what the predicate interprets. So you always interpret more and more elements. In the ultraproduct, this will become an infinite set, a discrete infinite closed-bounded set, but the resulting ultraproduct is no longer o-minimal because this is violated. The other characteristic in case of finite set is just the number of elements, and it gets bigger and bigger, so it's not uniform. That predicate is not uniform Euler characteristic. Okay, so I wanted to give one example. No, none of this is difficult. No, none of this is difficult. It's sometimes a bit lengthy, but none is really difficult, no. Okay, so I don't know, I won't have this example, but I want to say one thing. Okay, one thing that I need to say is, in these things, we need one more first-order property, and that's what you have to single out. Once you have that, you're okay. And so this is what I call DPP. So that's another first-order property that belongs to this theory, and is probably not, and you know, we know it's not everything. This says that for every F definable and D discrete, remember, discrete is finite, and if you have a map from a finite set to itself, if it's injective, it's surjective, and vice versa. The pigeonhole principle. So this is the same. So if F is injective, even only if it's surjective. But that's a first-order property. You can state that in first-order way, and this is therefore the discrete pigeonhole principle. Okay, and so this is a condition that you need to prove this, but you know it's there. So, and some people. For Nasiera thinks it follows from DCTC, but I have my doubts. I think it's stronger than that. I'm not sure. Okay, unfortunately, I cannot give an example of an application, but spirals would have been there. So I could treat spirals in this sentence. But okay, that's for later. Thank you very much.